Hello, I am Rob Koenen, one of the founders of Tiled Media, a pioneer in high-quality VR streaming solutions. I'm pleased to be able to do this talk together with Richard Mills from Sky VR. Together, we will explain how we deliver Sky's brand new VR football experience to Sky's customers.
We do live in interesting times. Who would have thought that streaming, rather than being at an event, would be a thing? That visits with your friends would be forbidden? Who would have thought you'd be able to co-view a real event in sync with your friends? Well, in 2016, Sky began experimenting with new ways of viewing and engagement in its key sports and entertainment offerings. Its research highlighted that a virtual viewing presence at events enhanced the fan experience. And all of this came together in Sky Worlds, just launched by Sky UK.
That's some breaking news from the Nürburgring.
The Smart. Marcus Smart from deep. Kane. Oh, yes.
Greenwood. Mason Greenwood. It's the substitute who's come to Manchester United's rescue.
Bespoke Sky immersive cameras are combined with the Sky UK Premier League match feed. Stats and scores are added to a console in the app, and Sky added co-viewing sync and live chat with your friends represented as avatars to the mix. Maximum quality and fast angle switching are key to the product. Sky partnered with Tiled Media to provide secure, low latency 4K plus resolution to Sky's Oculus Quest app. Let's have a look at the front end. Sky experimented with a range of camera systems, including 360 and 180 degree feeds. Blackmagic design cameras and broadcast infrastructure were eventually chosen. Remote production was a key requirement from the start, and BMD's compact, flexible products were ideally suited. Multiple events were used to trial the development of the product, and attention was paid to reliability and quality of output. Here's a few images from on the pitch and also within the control vehicle. Here's an overview of the video pathways within the outside broadcast vehicle. The UHD feeds come into a mixer where they're processed. The outside broadcast feed from the main match is then inserted, and the outputs are fed via contribution encoders over a broadcast switch and onto Sky's Master Control Room, MCR. The signals are then on-passed to ClearVR. Let's have a look now at the camera placement. A variety of camera positions were tested over a period of a whole football season. This is a fairly conventional layout. We have a camera, the main camera, at the halfway line in a high position, a camera behind each goal, and then one camera by the technical area of the manager's dugout. True immersion occurs when the viewer feels part of the crowd and has a unique insight into the event. In this layout, the main camera is again on the halfway line, cameras 2 and 3 are at the corners, and camera 4 is in the technical area opposite camera 1. Over the course of our testing, we experimented with a wide range of different camera positions. In this instance, the main camera is again on the centre line high, but the two cameras left and right are on the 18-yard line, with the camera opposite in the technical area. This is another popular layout, especially at smaller grounds, where the cameras are closer to the pitch. Camera 1 is again on the halfway line, and cameras 2 and 3 are behind the goals, often quite close. We know from our stats that the viewers do swap camera angles during the game and can follow the action as it nears one end or the other of the pitch.
Let's take a quick look at the contribution of the camera signals to the transcoder in the cloud. Let's look at the contribution. 4 HEVC encoders each encode the fisheye feeds at 70 megabits per second. An HLS packager then ensures these are packaged and contributed in perfect sync using program date time metadata. ClearVR Cloud acquires these streams using HLS pool, while a firewall and encryption provide security between Sky's master control room and ClearVR Cloud. Next up is the tiled transcoding. Let's look at the VR video. Here you see one, a 360 sphere represented as a 2x1 equi-rectangular projection. This is very much like you'd see a map of the Earth represented in a plane. Now in VR you only see a very small part of that picture, like typically an eighth or a sixth. This is called the viewport. So the first thing that we do is to cut up this video in tiles. Next, we determine which tiles are entirely or partially in the viewport. Then we only stream those tiles that are actually in the viewport. This has two main benefits. First, obviously, we save bandwidth because we only stream the pixels that are actually in the viewport. The second advantage is that we can use the decoder much more efficiently. Instead of decoding all the pixels that surround the user, we again only need to decode those pixels that are in the viewport. So this little trick allows us to use 8K source content while there's only a 4K decoder on the device. Next to these high-resolution foreground tiles, we also stream a much lower resolution background. And this is useful because when the user turns their head, they shouldn't see black while we retrieve the high-resolution tiles from the network. They always see something, and what they see is consistent with their head motion. Another important detail with tiled streaming is that we don't need to reload an entire viewport when the user moves their head a little bit. It suffices to just discard the tiles that went out of view, which are the red tiles in this picture, and load the green tiles which have just come into view. And all the other tiles, the ones that are in the middle, can just stay in the buffer and they can keep on playing. Well, this was easiest to explain on an equi-rectangular picture. In practice, we use a cube map rather than an equi-rectangular picture because it's a much more efficient representation. When we have extracted all these tiles, we need to encode them. They're all encoded as individual HEVC tile tracks, and these are packaged as MP4 files. And to allow for a good balance between fast switching and good quality, we have multiple GOP representations. And for the background, we have two, one for fast switching and one for high efficiency. This is mainly when we do camera switches. And for the foreground, we actually have 3 of these GOPs, with one intermediate GOP between the short GOP and the long GOP. And this is because you do a lot more tile switches when you look around. So the foreground needs to be able to be switched out much more frequently, but it also needs to be able to be encoded efficiently. So when all these tiles are added up, we get somewhere between 120 and 200 megabits per second worth of HEVC tracks. And that depends on the exact resolution, obviously, and also the recording angle, whether it's 180 or 360 video. Next up, the contribution to the origin server. To allow the content to be ingested into an Akamai origin server, we need a little bit of a trick. Akamai's MSL ingests have a limit of 45 megabits per second, and with 200 megabits per second worth of tiles, that's clearly not enough. And this is why we take 6 ingests in parallel for each of the camera feeds, and so for a live match with 4 cameras, we need 24 ingests in total. And then the last part of the end-to-end system, which is the actual distribution. To explain the distribution, we also need to talk about the application because it plays an intelligent and active role. The distribution uses pure HTTP retrieval, HTTP2, using multi-part byte range requests. This makes it extremely scalable as there are no per-client encoding systems or edge computing or anything like some other VR distribution systems use. A smart client knows exactly the capabilities of the device, the viewport, the network characteristics, and it's smart enough to determine what tiles to retrieve at which exact quality. It's also very robust. The client looks at the last possible moment, which tiles have arrived and which haven't, and then it rewrites the bitstream using only those snippets of bitstreams that have arrived and sends those to the decoder. And then rewriting everything into one single bitstream. This requires only one hardware decoder, which is why this trick can be done on all of today's mobile devices, basically. And this principle, also known as late binding, has been adopted in MPEG's omnidirectional media format as the advanced tiling profile, which is about to be published and has recently been approved in MPEG. Just a couple of statistics. The user bitrate is typically between 7 and 50 megabits per second, which obviously depends on the type of content, how often the user switches the camera, how frequently they move their head. And then a couple of latencies. So an important statistic is tile switching latency or motion to high resolution. This is the time between when the user moves their head and they see high resolution tiles. This is typically between 50 and 100 milliseconds, which is actually barely noticeable or not noticeable at all on a good network. The camera switching latency is in the same order, but you need to switch out more tiles, so it may take a few 100 milliseconds. And the end-to-end, glass-to-glass latency is now in the order of 40 seconds. It's not something we've optimized for. We're planning to get that down below 10, but it's also not been a priority of our customers to date. Just a few words on the security of the whole system. We already noted that the delivery from the master control room to our cloud platform was secured, and the same applies to the delivery to the user, which is governed by DRM. Last, but certainly not least, a few words on the application, as this is what ultimately determines the user experience. The application was built, and is actually still being built because this is an MVP, by Livelight VR, a company with a strong background in live VR sports production. So the application is available in the Oculus Quest store for the Quest 1 and 2, and it gives access to 12 linear TV channels, live matches in the weekend, and highlights after the weekend. Users can see live statistics, players, lineups, and these come in through Opta feeds. And moreover, they can join their friends in social rooms where they can use voice chat to talk about the match. Now, what's really important is that we keep those users in absolute sync so that they can't spoil each other's experience. And finally, a few words on the next steps, as this is the beginning of the journey, not the end of it. So we're now working on more sophisticated multi-user sync, where we have a smooth catch-up with just increasing the playout speed a little bit after people experience a little bit of buffering. Then we're improving the camera switching with a continuous audio track, so people have no fear at all of missing out. And this is also going to be the basis of more advanced adaptive bitrate methods. And then we are considering returning to Quick, which is now being deployed again. We did experiment quite a bit back in 2017 with Akamai, but at that time it was too early to implement, but it looks like it's making a comeback, and Quick is especially useful, as we found in our experiments back then, for users that are on less than perfect networks. Thanks very much, and let's see if there are any questions.